So we're going to continue with PET. Basic structure of the scanner, this is from the intro lecture, is it's a long, cylindrical tube. As we saw, it's going to have detectors all the way around. Unlike SPEC that had that, detector that was a flat panel and it rotated around, PET has a whole set of detectors always there. They're always on. And at the front of this scanner, this part right here is actually a CT machine. So the first thing you do with the patient when you do one of these studies is you take a CT. And so now you have essentially X-ray attenuation as a function of position, such that you can do very accurate calculations of what you expect the absorption of these, half MeV photons to be along any pathway. It's an expensive machine. So, PETs always have a CT attached to them now. I don't think you can get a PET scanner without a CT on the front end. And, they're a couple of $1,000,000, right, to do this. But that's not the super duper expensive part about PET, right? The thing about PET is you inject a radionuclide that emits positrons, which is expensive stuff. You have to have a particle accelerator to make those contrast agents. And that particle accelerator has to be on site, and it usually has to be very close to the PET scanner.
Do you need the same contrast for CT as well? Or
say that again?
Do you need contrast for CT as well?
No. CT, the contrast is an inert substance that just absorbs X-rays really well. So it has iodine in it usually, and so big electron cloud, and that absorbs X-rays. That's what CT contrast is. PET scanning, these are actual radioactive nuclei that their mode of decay is such that a positron will come out and will annihilate with an electron, right? So that's an expensive proposition. We'll look at a bit at how you make various agents in PET. There are dozens now of agents that you can inject into people and take a PET scan. So, for example, this fluorideoxyglucose, we'll look in detail at this atom or molecule actually, and the fluorine, so it's clicked on to a sugar, basically this fluorine, it replaces a hydroxy group, and the fluorine itself, the nucleus, is the thing that decays and lets off this positron. And the great thing about this, and we'll see a couple of examples of this, is that because it's a nucleus, so you can just put it into chemistry. Say it's a carbon nucleus or a fluorine nucleus, you just put it into chemistry that happens in the body under normal metabolism. So when you inject it into the patient, they take up this stuff just like it's a sugar or just like it's acetate or some other, organic molecule that their cells absorb, right? And so it just goes straight into the normal pathways. That's the power of these contrast agents, is that you can do actual organic chemistry in the patient and watch what's happening, right? I would say PET, the biggest use of PET is, and the reason the PET scanners here are in the cancer center, is because you look for metastatic disease with PET and cancer. And so that's probably the highest number of PET scans done each year is in cancer. And this fluorine 18 is actually good for that because cancer malignancies, it turns out, are metabolically upregulated. They're turning over metabolic molecules very quickly. And they're like hot, like literally they can be hot. Their temperature can be a little warmer than that around them, and they're burning sugar a lot. And so if you inject this fluorine 18, it will go to those neoplasms, right? Because they're upregulated. So if you do a huge round of chemotherapy, whatever, and then you go back and image the patient and all those hot spots are gone, well, that's a great sign, right? So that's often done. In cardiac, we're going to focus on the heart and mostly focused on perfusion. So is there blood flow going to the myocardium? Because for the last 50 years or 100 years, maybe even, of cardiovascular research and cardiovascular disease, the thinking was, the group thought was, myocardial perfusion is the fundamental thing that we would like to know in order to determine if this person requires aggressive therapy or not, right? That turns out may not be true. And it just in the last 5 years, 5 to 8 years, it's been shown with these large clinical studies that that just might not be true, that myocardial perfusion may not be the most fundamental thing you want to measure to determine a person's future risk. And the reason for that is that if you have, and we've talked about this a bit before, if you have low perfusion, that can essentially entrain the tissue to then be resistant to high perfusion deficits, right? And so it might be protective to have low perfusion in a chronic way. And it turns out when you look at the data from the ischemia trial and you ask who is most probable to have a fatal event, it turns out that the nuclear medicine data is inverted. The people who have lower perfusion deficits seem to be more probable to have fatal events than the people who have higher perfusion deficits on a chronic time scale, right? Which when you're looking at the data, you're just like, well, that doesn't, the first time I saw it, I was like, well, this is, I thought I told you nuclear medicine was, because this doesn't make any sense, but it kind of does make sense in the end, right? When you look at the whole model. Turns out the only thing that really predicts really well who's going to have a catastrophic event is a CT estimate of how many lesions do you have. Do you have 10 lesions? If you have 10 lesions, you're kind of toast. If you have 1 or 2, it's better, you know. But so just to review, here we have this fluorine 18, or it's going to decay into oxygen 18. It's going to emit a positron in that decay, and then that positron will wander around through the water and cells and stuff around it until it finds an electron, or it loses enough energy such that when it comes in contact with an electron, they annihilate each other, right? It's not a 2-micron dot. It can wander millimeters in the tissue before it finds a electron pair, right? Which is a source of blurring, obviously, right? Because you have a source and then it's going to wander away from the source and then annihilate. This molecule has a long half-life. So after 110 minutes, you're down to half the stuff left. Then 110 minutes after that, you're down to a quarter of the stuff left, right? And so it's around for quite some time, which makes it less stressful in taking the agent and getting it into the patient, or taking the agent, making it a biochemical element or molecule, and then putting it in the patient. You have time to do all that. Whereas we'll see in some of these positron emitters, their half-life is like 2.5 minutes. So everybody's got to be hopping. When that stuff comes out, you got to do stuff fast, get into the patient fast.
For this positron, is it where it's tracking its trajectory? Or is it emitting high energy, right? Is that detectable or no?
The energy at which the positron is emitted, so it's kinetic energy. So it comes off of the nucleus with some speed, right? And so it has kinetic energy. And it depends on the nucleus what that average kinetic energy is when it comes out. There's a variation. My short answer would be no, in that, this is a nuclear event. It's like a decay that is a random event. The thing comes off at a random energy. I'm not sure it's tied to anything that we really care about or want to know in terms of cardiovascular disease. Excuse me. However, we just like, oh, that's useless. Like 10 years from now, somebody shows it's really useful information. So
I'm thinking like there's no electronic path so far.
Oh, like I see the density of electrons around it. Yeah, maybe. Okay. And remember, the wonderful thing also about this imaging technology is that we do coincidence detection. So we have detectors in an array on either side where the one photon comes up here, boink, I get a spike. Another photon goes down here, boink, I get a spike. If they're close enough in time, then I say that's a coincidence. And then I chalk that up to an event. And I say, well, my positron was emitted somewhere along this very thin straight line, right? So it's highly localized. It's not localized in this dimension, obviously, but it's highly localized in the axial dimension around that line. And we use these as lines in projections to then create a 3D image, right? What else is to know about that? So light travels, remember it's like 3 times 10 to the 8th meters per second. That's how fast light travels. So you just look and say, well, how far does it travel? And say a nanosecond, right? So in a nanosecond, it's going to travel about 30 centimeters. So it's, about this distance here. So, when we hit these two events, we kind of want nanosecond temporal resolution on our detector, which is like a gigahertz, right? Sort of scope. If I have a gigahertz scope that I can see things. So it's pretty fast. Things are happening pretty fast. And then we'll see what the also thing that we have to take into consideration is this will produce a flash of light, that large energy photon, the half MeV photon causes a flash of light in a crystal, just the way it did in SPECT, basically. And then we're going to figure out where that flash happened using the same techniques we did in SPECT. So the crystal has to be a little bit thick, a few centimeters thick, because it's a high energy photon and they tend to go through stuff, right? And so that's gives you a loss of resolution because the crystals are thick. The two modes that you can run the scanner in is if you want individual slices, we looked at this before, you can put sepia in here to cut down your sensitivity to individual slices. Or just go full on 3D where any event along here, if I get a coincident event with this detector position and any of these, I know which line it came from in 3D. And that's usually the way it's done nowadays. What can go wrong? Here's 3 instances of events occurring. One of them is perfect in that I get bing, a positron comes out, hits an electron, we get an event, photon comes off this way, photon comes off this way. They have the right amount of energy, so they get through the energy threshold, and they are close enough in time that you say they're coincident. Okay, so that's great. So now I draw that line, right? And I just record that I have an event along that line, right? And I'm just going to do the PET, basically the raw data at the end is just all those lines in time, right? Just which line. So you have detector pair and an event and just and it's just a list. That's the data for the raw data. If I have my creation of the 2 photons here, so half MeV photon comes this way, half goes this way, it interacts with something in the sample, scatters. So photons will hit electrons on their way out, hit nuclei, not very often, but they'll hit things like that, and scatter off at a different angle. They obviously have a lower energy when they scatter off because they've imparted some energy to whatever they collided with, right? So that thing shoots off with kinetic energy or another photon or something. And then this comes off, and now say it's a 1 MeV photon, right? Going this way. So then I get an element or an event here, they are coincident, right? If their energies are really different, then you say, okay, one of them scattered, so I shouldn't take it, because when I reconstruct that line, that's the wrong line, right? It actually should have wound up over here, right? So not a good plan. However, if it only loses, 5% of its energy or something, it winds up here, then you do have this wrong line in there. And so that will create a kind of haze in the background of scattered radiation causing just this background haze of events. Now, this isn't going to happen too often, but it's particularly cool that it can't happen at all, is that I have detection this way, or an event here, right? Annihilation here, and they are essentially coincident, okay, in time. Those two annihilation events are coincident. So now I have 4 photons flying, right? And when they hit their various detectors around here, I have 4 things. So I can create lines of response that are incorrect from that. So should we throw it out? You could throw it out. You can imagine, well, let's keep it and we'll try it with different combinations until the image gets better, right? But probably just throw it out, right? Because you want to avoid having the wrong line across there. Okay. So those are a few ways that goes wrong. The detector itself is very much like those detectors we saw for SPECT. At the front end, you have something that captures a photon. Remember in SPECT, it was like a 140 keV photon, or what was it? It was 160. Came in, caused a flash of light. Then the photomultiplier tube causes a big electric pulse. So if I have 4 photomultiplier tubes that are neighbors here like this, they're in this square. And above it, I have an 8x8 array of these scintillation crystals. And so when a photon goes through from any direction, like it can come up here, doink, and cause a flash of light here, this at the bottom of the crystal will have a kind of a spread light, and the photomultiplier tubes will all have voltages that come out of that. And we'll use that averaging, the spatial averaging we did in SPECT, to determine which one of these crystals we think that event occurred inside. Okay. So if you remember, so if I have an event in here, it causes a flash of light. I'm going to get a strong signal in this photomultiplier tube and very weak signals in the other 3. And so it's going to place it up here. On the other hand, if I have one that's right in the middle, these 2 on the bottom will have weak signals. These 2 on the top will have equally, and the amplitude will be the same. So we say, well, it must have come from this position. So that's how we piece together the positioning of our events, which is the detection of that half MeV photon, right? Time windows for that detection. So these things are bismuth that germinate. It looks like this. And, it has a cross section for capturing photons at this energy. So the flash lasts for 12 nanoseconds. Okay, so you have a flash of light, goes up to its peak number of light photon amplitude, and then it decays away. And that decay away, the half height or something of that decay is about 12 nanoseconds. Okay, so remember, let's go back. How long did it take a photon to get from our event out to the detector? It took about 1 nanosecond, right? So now we have a nanosecond, and we got a flash of 12 nanoseconds. So we're going to saturate our detectors if we just do it as fast as we can, right? So there are other new detector materials where they use really smart chemistry to make something that has a higher decay rate of the light coming out. And so for this LSO detectors, apparently you can cut it in half to 4 nanoseconds. So now 4 nanoseconds is about photon flight across the whole scanner. So that's pretty good, right? Any questions about that stuff? So just this is a review basically, that in SPECT, we had this structure inside the camera with the sepia and an anti-scatter grid such that all of the signals coming out of here we assumed were from these straight lines, right? So we threw away a ton of photons, right? All the photons coming at different angles like this, we just chucked them out. We only took these ones coming in perpendicular to the anti-scatter grid. In PET, we can just leave everything open and just sample with high enough frequency such that we can detect coherence or coincidence, I should say, and then make these lines afterwards just by resorting everything. So when I make a set of parallel detection lines, these are all of the events that simultaneously this detector and this detector recorded came from along this line. So basically, I have data for the projection along that line just by looking at those two detectors and saying, how many points did I get here? And that gives me an amplitude, right? And if I do that, if I look down my whole list, say, okay, what about this one and this one? That gives me another line. I can just create basically a projection function at a specific angle just by, looking at detector pairs and where their coincident events occurred. So after I collect all my data, that's what we do. We just go through the list and we create these projection profiles from that list mode data. Well, this is just review of what can go wrong in that in the Z direction, if I have detectors along here and I have an event, I can get a scatter so that I get an incorrect line of response, but we've already done that. Okay. Yeah, sure.
I'm not sure if we understood the right setup. So are we then going through all angles to make sure we have each detector with the opposite with another detector?
Exactly. So I mean, I have a list of coincident events. And so on that list, I have two detectors named and said this detector and this detector. So I look through my list at when those two detectors were checked off as a coincident event, right? And I just look down my list and say, oh, I had 100 of those. 100 times I had this. And so when I'm creating a profile that is this projection, those two detectors go in and I just put 100 in that position. And then I move over here and now I have two new detector elements and say, how many coincident events did I get in those two? Say 50. So now I just plot that as a function of position along there. And that's how I reconstruct my projections.
And after doing it for all of these detectors, the way it's shown there, would we have to expand or make the angle bigger or smaller so we also cover other angles like say
Yep, absolutely. So, but you can imagine all my, let's just look at one detector. If I look at this detector and all of its possible companions who give me coincident detection. So let's say this one and this one and this one and this one and this. I'm clicking through angles, basically. And so if I click through all detector pairs, I click through a lot of angles. Right?
so pretty fast.
Pardon me?
Assuming it's server fast, so how long does the whole process take?
Oh, well, that you can do pretty quickly, right? Because it's just a list of numbers. And so you can put the list into projections very quickly. The time-consuming step after that is actually the inversion from the projections to the image. And so now I have a whole set of projections. It's just like CT raw data, SPECT raw data, got a set of projections, and now I want to create a picture from those projections. That's the thing that usually, or used to, take a long time because, as we'll see, you use iterative techniques. You take a guess and you look and say, if my image was this perfect image that I have here, what would my raw data look like? You forward project your image estimate and look at the raw data and say, what are the differences between the actual raw data I have, right? And then you correct those differences and make a new guess at the image. And you just iterate on that loop. And that takes a while. That takes like half an hour or something, or used to. And inside there, you also compensate for the fact that some of these projections will have a lot more material that causes more absorption. So you put that in your model as well. You put scattering in your model, all these things. But then you do that like 10,000 times. And you do those really expensive models 10,000 times. And then you use that as ground truth data. And you train a new neural network. Say, here's a list. Here's the image I want. And the network will just do it.
You mentioned too that for CT companies are very protective of the model they use. Was MRI usually public? Was it on the
A PET is a lot more open because PET is principally done in sort of advanced university medical schools. So the difference between SPECT, I think it's like 10 million scans a year are done, and PET cardiac is like 200,000, right? So it's because you need a cyclotron, right? So cardiac, to be perfectly honest, cardiac PET is usually an invited guest by the cancer center to come and do cardiac. If you have some special patient you want to do perfusion in, we'll let you use the PET scanner to do the cardiac. But it's mostly used in cancer, right? So, but
Then you would have to have some fire indication, right?
usually they would want to do, there's some applications which are like metabolic imaging. It's like, is the tissue alive? Think about that, not what's the blood flow in this tissue? The question is, are the cells in that chunk of tissue still alive? That's kind of a cool question, right? Or is it an infarct? Are they dead and it's just scar tissue, right? And early on in ischemia, if you have a heart attack and say you're sitting in a hospital bed and they haven't done the intervention yet, and they're trying to decide, what do I put in 3 stents? Do I, what's the culprit lesion, all of this kind of stuff. Then they take you to PET, and there's a chunk of tissue distal to your circ that is dead, right? It's gone. There's no metabolic activity in it anymore, but it's still young enough, the infarct is young enough that the tissue hasn't really changed its morphology. It's not thinned out and stuff like that. Then the question there is, well, why put a stent down there? Because the tissue's dead, it's not coming back, right? So this is like viable tissue imaging. So that's kind of where PET goes. If you really have a reason to do viability imaging, I would say that's where it's a key. Especially this post-ischemia trial where PET can measure perfusion much better than SPECT because it's much higher resolution and it does better contrast agents. But the question now is like, is that necessary? Do you really need that kind of resolution for perfusion? That's still an open question. But getting back to your question, PET manufacturers are much more open to cooperating with universities to do research because this imaging technology really came out of universities. In fact, it came out of UCLA, right? So UCLA was the driving force in making PET something we could all do. And I would say probably 90% of the IP for PET came out of the labs up there. And so it had a long history of interaction, right? CT, on the other hand, started in industry, right? And it stayed in industrial labs, like so that when I go to there's a CT conference every other year where all of the people who really know how to do CT come, and there's 250 of them. This is for the world, right? It's 250, 300 of those people. And I would say 50% of those people, maybe 75% of those people are in industry. And they still come together because they're geeks, right? And they like to show off what they're doing. It's so cool and everything. But they're, it's a small community and it's a lockdown IP community. So, and they all have their own, and it's interesting, they've all sort of gone their own way in various solutions in CT. So we'll see when we do it, like all the scanners are kind of different, right? They've come up with their own solutions. So I don't know. To get data out of companies in CT is just you've got to really have a good reason that they're really interested in where the product is going. Not just, oh, that would be curious, let's do that. It's like we're MR on the other hand, it's just there's I think 3 to 4,000 people go to ISMRAM every year, right? And most of them, huh? Yeah, most of them are in university labs and have the company, each company has a room like this in their factory. And they bring professors and grad students and postdocs into the room every 4 weeks and they give a course on how to program their scanner, right? And so you take that course and then you go home, you have this big binder. Well, not anymore, but you had a big binder, and from then on, you were your own, MRI programmer. You could do whatever you want with a scanner, including overheat it, put amplitudes that were too big, stick amplifiers into resonance, all these bad things you could do. So you had to sign off and say, if I blow the scanner up, we'll pay for the part. We won't just like call service and say, hey, can you come give us a new X gradient? So anyway, so spatial resolution for PET on a, sort of order of magnitude is 5 mm foot width to half max. So that means if I have a little vitamin pill, it's 1 mm or 2 mm across, and it's full of some positron emitting stuff, and I drop it in the scanner, put it in the scanner, I'm going to see an image that is a Gaussian that has a 5 mm full width at half max. That's what I'm going to see for that object. And so you convolve it, everything that is the ground truth, where all of these positron emitters are, convolve that with this Gaussian, 3D Gaussian, right? And that's your spatial resolution of a PET scanner, which is pretty good because for SPECT, it's about 10, right? This is like twice the blurring in SPECT. So the intrinsic spatial resolution of the detectors themselves, those crystals, so the geometry of those crystals actually is the primary reason you get all this blurring. The distance traveled by the positron depends on the energy of the positron. It depends on the nucleus. We'll see a little chart about that. And remember, we saw that it was 180 degrees plus or minus like 0.3 degrees. That blurs it a little bit, but not as much as the actual geometry of these crystals. And you can see that here. So I mean, this is a complete exaggeration, right, geometrically, but just to make the point. But if we have a cylindrical, like a donut of these crystals around in a circle like this, and the thickness of the crystals is this direction, right? You can see that if I have a coincident event between this one and this one, right, there is a much larger sort of possibility of LORs that fit between those two crystals than there is for between this crystal and this crystal, just by the geometry. So the two crystals that are facing each other obviously are honed down and focused towards the center. If I have an event somewhere in here and this crystal lights up, remember, I can hit this crystal anywhere. I can hit it down here. I can hit it up here. It's going to cause a flash of light the same way. So I can hit this one down here and this at the same time, right? So ideally, these would be infinitesimally thin and we wouldn't have this problem, but we wouldn't collect any photons. Nothing would interact, right? So you have to have enough stuff for the photon to interact with. Okay. Okay, so you have a geometrical sensitivity for your spatial resolution. Everything towards the center is obviously going to have higher spatial resolution than stuff out towards the edges. And so here's some positron emitting radionuclides commonly used in PET. And as you can see, they're all sort of these really nice molecules like carbon, nitrogen, oxygen, stuff that happens in biochemistry all the time, right? So if you can put carbon 11, which is not normal carbon, right? It basically it's radioactive carbon, right? It has a half-life of 20 minutes and it ejects a positron, right? The energy that comes out is about an MeV, like it's booking, right? And this is its maximum range in millimeters. Now that is not, if I have a source and it's truly a point, it's going to be a Gaussian density around that point, right? And this is, they're saying maximum range. I don't know what that means. That probably means like 99% of all the positrons are in a sphere that has a radius of 4.2 millimeters, right? But ideally, you could give the full width half max of the Gaussian, and it's probably about half that, right? So it's like 2 millimeters. Like 70% of them are within a sphere of 2 millimeters. Still a source of blurring, though, right? You know, if we wanted to do PET imaging of coronary arteries and the wall of the coronary artery, that would be cool. Like, because you could do the metabolism of the vessel wall, but you know, blurring it by 2 millimeters, you know, it's going to make it kind of a blurry picture of a vessel wall. So that's carbon, nitrogen 13, oxygen 15. This one only has a half-life of 2 minutes. So that guy, you got to really be ready to go. But you can put this in water, like H2O. And if it's H2O with oxygen 15, that gives you a tracer when you inject it into the patient that's just water, right? So that will go everywhere. It's not like the blood-brain barrier isn't a problem. It goes straight into the tissue right away. It just diffuses like water. So that's terrific. It can go right through a cell, you know. So if you want something that's freely diffusible, that's a great choice. And then F18 is this molecule, fluoride deoxyglucose, which is like a sugar, and rubidium. I don't know what this is used for, actually. I should have looked that up. So this is, you know, you have the scanner, right? Which is down the hall from this thing, right? So when you decide to buy one of these, you need a place to put the scanner. Space is an issue in most academic medical institutions and all medical institutions, right? And then you got to put this darn thing somewhere, and it's got to be close, right? So this is a particle accelerator, and it's used to create these agents like F18, N13, all that stuff. And you can see he's using robotic arms here because he's doing chemistry with these elements that are highly radioactive, right? So you have to have it in a chamber that you can manipulate the stuff, but all the radiation stays in the chamber, right? And this guy has to do his chemistry really fast, mix it up while it's decaying in its activity, and stick it into a bottle that can be sucked into a syringe and put in the patient, right? And normally there's some kind of rapid transit from this location to the scanner. There could be like one of those vacuum tubes that goes, and the stuff goes down the hall really fast, depending, right? If you're doing O15, obviously you need that. But, you know, you can image amyloid plaques in Alzheimer's disease. You can, a lot of dementia, seizure, cancer, all this stuff is available. So how do you, in this machine, what the heck do you do to make these elements? So I just picked carbon 11 because carbon you can put on any, you know, organic molecule, right? And oftentimes it's used to produce acetate, which is in the Krebs cycle of you know, metabolic activity of cells, right? And so the acetate just goes in and it has the carbon-11 on it. And so what happens is you have a proton beam and you hit one of these, you make in your target a gas, and it's either boron-11 gas or it's like nitrogen-14 gas, right? And then you fire the protons through that gas at a very high energy, such that when they interact, right, when the proton interacts with the nitrogen-14, it comes in, hits the nitrogen-14, knocks an alpha particle out, which is a helium atom, and leaves behind carbon-11. And so you just keep doing that until you have enough carbon-11, right? And then usually there's some kind of chemistry that traps the carbon-11 out of the gas, and you elute it down into some chemistry experiment, right? So you can imagine in order to get F-18, I have some different target here, but I bombard it with, it could be protons, I could bombard it with alpha particles, whatever. That's the basic process by which it's done. And then once you've got the chemistry done, you say you put C11 into an acetate molecule, right? And those of you who have Krebs cycle memorized in your head and you see where everything is, right? You know where the acetate comes in. I don't, but you could just like say, ChatGPT, show me the Krebs cycle. It'll show it to you. So you inject this stuff, and then the myocytes pick it up, right? Because it's this metabolic compound, and then it's converted metabolically in the cell into this, right? And so you not only get the amount that goes into the cell, which is proportional to flow into those cells, you also get the rate of conversion of this molecule, right, by the cell. So it's like how much metabolic activity is going on in the cell, right? And so it gives you a couple of things. The input gives you flow, and then the rate of output, it shows the radioactive decay of the substance, but also the rate of oxygen consumption in the heart. So this is why it's theoretically much more powerful than SPECT or CT for that matter, right? Because you can do these metabolic/physiology experiments with these tracers. It's pretty cool, right? I mean, it's, in terms of imaging technologies, this is right up there in terms of the, amazing things that humans have figured out how to do, right? So we're going to look at, I'm just going to tell you the number, and that is when I have an event, positron comes out, bing, annihilation, here come my photons. It turns out that only 15% of those positron annihilation events and the photon pair, 15% of those get out of the patient without a collision or a scatter. And so it's not that many, right? Because both of them have to make it out, right? So you want your detection to be high efficiency because the scattering of these things is a high rate, okay? Because you got to get two of them. They both have to escape. And the interesting thing, and this might be in a problem set, I don't know, but you can imagine if I had an event down here, say, the probability of the photon that's going this way getting out is very high, right? Because there isn't a heck of a lot of tissue between here and the exit before flying through space. But the probability of the photon going all the way through the patient and getting out here is much, much lower, right? But what's really interesting is that the joint probability of them both getting out and causing a coincident event is independent of where that event happens on that line, right? So basically you've got high probability, low probability, 50-50 probability in the middle, and that's your probability all the way along the line, right? So you don't have to worry about this depth dependent probability of getting a coincident event. They just self-normalize that way because it's these two photons, right? So it's like a self-normalizing depth compensation. Okay, so we'll do a quick comparison. SPECT, oh, it's 9 million. I thought it was 10 million a year in the US. So that's a lot of studies, right? That's heavy duty. If you think back to the maybe 2007, they were reimbursed at $1,400 a study. So this is a significant expense in healthcare, right? Just all over, right? So PET is only 200,000 a year. And that's because you have to come to a place like UCSD or UCLA or something like that in order to have a PET scanner available for cardiac imaging. It isn't found in cardiac or in cardiologist office. It would have to be a very big office, right? So here we make projections through collimation. Here we make projections through those coincident lists. Both, once we have those projections, we use the same methods for iterative back projection and we use the X-ray image in both cases for doing a calculation of the probability of scattering. These photon energies about 100 to 200 keV positron emitters, as we looked at. 4 to 5. This has about 10 millimeter for a technetium 99, which is the one we looked at a 30 centimeter diameter. Less attenuation because we only have one photon to get out. That's about it, I think. So we looked at this last time quickly. So here's the CT scan done before we take the PET data. Here's the raw PET data, just without any kind of data smoothing, anything, just make the projections and do a standard convolution back projection algorithm with a ramp filter. So no specialized filters or iterative stuff. So this is kind of the raw inversion of that data. So this could be a good first guess for an iterative algorithm, because when you look at it as a human, right, and you look at this, you say, hey, wait a minute, there's all of this bumpy stuff. Do I truly believe that this dot that's bright and this dot that's bright and this dot that's bright, is that real? It turns out it's not real. It's noise amplified by the fact you're doing a ramp filter. So you get a kind of noisy estimate of the picture. And so a smart person would say, I don't believe that's what's going on. We're going to do the physics modeling of what's going on and iterate until we get a picture that is more realistic, right? And you can do this in phantoms, right? Such that underneath what the activity is. You put a ring, say a water ring, in a PET scanner, and in the water you inject the PET agent, you stick it in, image it, right? You know what the underlying image now is. And it too will have all of this crud on it. And you just iterate until you get a better picture of the ring. And then you copy that algorithm over here to generate what you believe is a much more confident estimate of what's going on underneath there. And then once we have those really expensive physics based, inversions of this stuff, we use those as the ground truth to teach deep learning. So it becomes really cheap at that point, which is great. I mean, that, it used to be you had to buy $100,000 computer. Imagine that, $100,000 computer for every scanner just to do the recon, this iterative recon. So you got it done in 20 minutes or something. Now you can buy a $40 computer and just boom, it'll do the recons for you. And so here's these look just like those SPECT stress rest images that we saw, except they're much higher resolution, right? You have a much more confident wall dimension. Here you would say, look, there is some kind of lower perfusion here, right? There's obviously, we're gone here under stress. There's just no blood getting there. and then it resolves at rest. So this is something that will resolve itself. So that's a different type of perfusion than a fixed defect that just never gets any blood flow. This can get blood flow once we get back to rest. And the slope of this curve here, when taken into account what the injection of the contrast agent, this is what the counts in the left ventricle, right? So as soon as we inject this stuff and it comes into the left ventricle, we get very high counts in the left ventricle. There's a lot in the blood pool, right? And then it decays away in that blood pool. That function is our input function for what can go into the myocardium, right? So it's important to know this function, because if this was twice as high, we would expect the myocardium to actually be twice as high. So you need to normalize your estimate of uptake of this contrast in the myocardium to whatever is feeding the myocardium, which in this case is the blood in the left ventricle. Goes up in the aorta and then goes down the coronaries and goes into the myocardium. So you need those two curves. And if you have those two curves, both the input function and the myocardium function, you can actually compute how much flow is going in there. The actual mils per gram per minute of blood that is going into each tissue like box. So this slope is a key parameter for the uptake and the flow going into the myocardium. You can imagine if the slope's really steep, it's perfusing the myocardium very quickly. If on the other side of the heart, this thing looks like this, the slope is lower, it doesn't get to the same amplitude, it's a curve that looks like that, then that flow is going to be lower, right? There's just less blood getting into that tissue. So the baseline here, or it gets up to this plateau and sits at this plateau. And if you're doing acetate imaging, this is kind of how much acetate did the myocardium take up? Like just what is the concentration that it actually got to take that up? Same deal. This is what is this is water, right? So water, freely diffusible, goes into the left ventricle, right? And decays away. And then this is what it looks like in the tissue. Yeah.
Intuitive to me that we're essentially normalizing the patient's data with itself.
Yes.
Because if the heart is dysfunctional, wouldn't we get a low and left ventricle curve?
We would, but you would like to attribute that to the fact that their heart is dysfunctional, as opposed to the state of the vessels that are responsible for the flow. So if in that patient who has low function, you can't penalize their vessels, right, for having slow perfusion, when in fact it's the left ventricle that's causing the problem because it's not pumping enough blood, right? So you do need to say, how much blood could I possibly get down the coronaries? And we look at the signal in the left ventricle or the aorta and say, okay, this is my input function. Some patients have a very steep, fast input function because their heart is beating very well. Others, that input function will be delayed and slow because, go ahead.
What if it's the arteries that are causing the dysfunction?
Then you would see a further diminution of response in addition to the diminution from the left ventricle. So it would be relative to what it has to pump, right? So if my input function is twice as much, I expect my tissue to be twice as much, right? So you do want to self-normalize that data. That's a good point. I mean, if you don't, and you say, oh, I'm just going to look at perfusion here, patient to patient to patient, you'll get a lot of variability, and some of that variability is due to vessels. Some of that variability is due to the fact their heart isn't pumping well, right? So that's called the input function. And usually you can do it. It's dangerous to do this, but you can take the input function and basically extract it out. So if I have a perfusion that looks like this over time, it goes up and then goes down over time, right? And I want it, and I'm asking myself, how much of this slope up and this decay down is due to the vascular stuff, and how much is due to my input function, right? So suppose my input function looked like this. It comes, it goes to a huge value, and then goes to 0, and then goes down. Okay. And then I look at the vascular function, and it looks like this. So what percentage of that function that is my vascular function could you attribute to the flow in the vessels versus the cardiac function? If my input function was boom, one huge spike, and then bang, back down to 0. That input function is called, think back to electrical engineering. So that input function is called a delta function, right? Remember that? So if I have a linear system and I want to see what does my linear system do to a very small signal, right? It gives me a blur, right? And so if I can put a delta function and I can measure perfectly what that blur is, but I can't. The underlying left ventricular function also has a signal that looks like this. But you can take your tissue function and extract out that input function to see what is the characteristic of my flow function. It's going to be delayed, right? Some amount, right, from my input function, and it's going to have an amplitude change. So just like a point spread function in imaging, right? If I suppose I want to ask how much of my Gaussian blur, right, is caused by my imaging system. The function I put into the imaging system is a tiny dot. It's a delta function. And then it says whatever, bunch of things that happen to that signal along the way, my output image looks like a fuzzy Gaussian. That Gaussian, right, is due to the imaging system because the function I put in was a tiny dot, right? If, on the other hand, I put a Gaussian into the system, right, then I'm going to get out another Gaussian, a blurred Gaussian, but it'll be a little bit wider than the one I achieved with my tiny dot. And the reason it's a little bit wider is because my input had a little bit of blur on it, right? So you can subtract out that blur to figure out what the blur is for the whole system, right? It's dangerous to do, though, because it's very sensitive to noise. So anyway, we don't get delta functions when we inject contrast agents because usually you put it in a vein, it goes into the right heart, goes out the pulmonary artery, goes into the lungs, right, and gets mixed and spread out in the vascular tree of the lungs, right, then collects back up, right, comes back down into the heart, into the, who knows where it goes, the left atrium. From the lungs, it goes, there's 4 big pipes that go into the left atrium from the lungs. Stuff all pours down into the left atrium and then gets sucked into the left ventricle as a big bolus, right? Ejected out into the aorta and then down the coronaries, right? So that whole process basically blurs that input function a lot because the lungs, for instance, like if I put a delta function of contrast into the lungs, it's going to take different pathways and come out at slightly delayed time. So it'll blur it. So somebody's pulmonary health can affect a lot their input function, right? If they have a lot of pulmonary resistance, for example, something like that. Okay, so here, this is, again, O2 water, O15 water. So it's a positron emitter that now is in a water molecule, And what you can do is you make this estimate of relative amount of flow as a function of position in the myocardium. So all we're going to look at is like, what is the slope, the upslope, and the peak of the contrast? And those will go into a model to determine the relative amount of flow. And this is all relative here. So here's 100%. So this is the part of the heart that is getting the maximum amount of flow. It's getting the highest signal that we're seeing. So if we go back to this will be the highest. It'll go up the highest. It'll go probably the fastest up there, right? That'll be this. And then over here, we're getting 50% of that. So if I go back to this, the curve would look something like this. It would not go up as fast. It would go up to about half the height, and it would go down like this, right? So it's pretty simple. It's just like not as much stuff got there, right? And that's over here. And then here, we're down to 20%. So it's a very low amplitude signal on our data. And those voxels, we would see it's down here somewhere, right? So I make that map, and this is the percentage of blood flow as a function of position in the heart. Recall, this is called a bullseye plot. This circle is the apex, or the tip of the heart down here, right? So my heart's sitting in my chest like this, and the apex is the point, right? And the base is where the valves are, the aorta and the mitral valve. Apex, I move up towards the base as I go radially out on these diagrams. And so this is the base as a function of position around the heart. This is called the lateral wall, which is on the left side of the patient, on their left arm over here. And then if I look this way, I'm looking at the septum of the heart, or the right side over here. So basically, I'm standing at the patient's feet, looking towards their head. They're lying on their back. Okay. And this is their chest wall up here, the anterior wall of the heart. This is their spine down here. This is the posterior wall. Left arm, left side of the heart, lateral wall, right side is the septum. So it's a nice way to map the full 2D surface of the heart onto a flat, thing that you can carry around with you. Obviously, it distorts the actual size of things. I mean, this is a huge signal, but it's, because it's at the edge and been flapped out, it's bigger. It's like northern Canada on a map, right? It looks huge space, right? Or Antarctica. But what we can do, we go back here and we say, you know what we're going to do? We're going to take our input function, right? And we're going to actually normalize this curve to the input function so that we can detect how many milliliters per gram per minute of blood is actually flowing into each part of the heart. So we'll make a map that is that. And so it's not relative to other parts of the heart. It's just an absolute number. Right? And then these are the numbers for this patient that come out. And you look at it and go, damn, it's pretty uniform, right? And if this is the stress image, I don't know if this is, it might be. But if this is the stress image, for example, we're seeing like 1 milliliter per gram per minute under stress, under adenosine stress. Not good, right? Because you basically should be up at 4 or 5 at that point. And so the entire heart is underperfused. And so that probably means this patient has triple vessel disease, which means they have a large, significant infarct in their right coronary artery, in their circumflex, and in their LAD. They got 3 lesions cutting down the flow everywhere. Because it's not creating a huge gradient in flow. Okay, so that's absolute flow, which is most accurately and reproducibly done by PET. Okay, you can do it in nuclear medicine, not as well because the resolution and everything is not as good. here's an example of a vascular image. This isn't a cardiac image, but it's an image of somebody's carotid artery. And so here's the CT that was taken first, and then overlaid on top of the CT is a PET F18 FDG image. And FDG is a sugar in which a hydroxyl group has been replaced with this F18 molecule. So I think, yeah, here. So this is just a standard sugar. This was a hydroxyl group. It's now an F18 molecule, and such. This gets absorbed like it's a sugar into the cell because the cell wants it, but it doesn't get metabolized because the metabolic processes get screwed up by this thing. So it just sits there in the cell. So if you have really high metabolism, it will take this stuff up really quickly, right? And it just gets trapped in the cell because the molecule itself does not get converted through normal metabolic processes. And so here you've got this bright signal in the carotid artery, and that correlates with this thing here, which is basically a lesion that has been shown to have large inflammation and a lot of macrophage invasion, right? So B cells, T cells, things like that are going in there to try and kill what's ever in there, right? So it's getting inflamed. It's like, when you have a small cut on your finger sometimes, and you weren't quick enough with the neosporin or whatever, and the thing starts swelling, it gets pressurized and it gets hot, right? And that's macrophage invasion into that tissue, and the same thing happens to your vessels, right? So you could have a small injury, then there's macrophage invasion into that part. And so this is detecting that significant coronary lesion and active macrophage invasion. If you could do this in the coronaries, it probably a pretty good thing, right? It would probably a good thing to do if you could do it in the coronaries. People are trying, but the resolution is kind of on the limits of that. With a full width at half max of 5 millimeters, and the coronaries are moving, you got an issue. Here, this carotid artery doesn't move, right? So basically you can fix the patient's head and their neck and everything. Just tell them to stay really still and they can do it. And the heart, they're breathing, the heart's going up and down, it's contracting, and so your resolution isn't as good. And here's as I was telling you before, this FDG gets taken up by tumors, and you can see in this liver, there's a heck of a lot of FDG activity in this liver, right? So I don't know where the primary tumor was, but if it was in their brain, this is a big problem, right? And that it's now moved into their liver.